Hey folks, in this video we're looking at problem number 3 on group project 1, where we're simply asking which of these molecules is polar and what the direction of the dipole moment vector might be. All right, so I've already gone through, because we have already looked at the Lewis structures for these 3 molecules, so I've already drawn them here so we don't have to go back and go through that process. The sulfur tetrafluoride we have in problem number 1. This is a structure, it's the seesaw structure based on the trigonal bipyramid, of course, and we see this where we've got the dashed wedge thing. The dashed wedge thing means is when we see the dash, that means the fluorine is extending beyond the plane of the display here, and the wedge means it's out in front of the plane. We just simply do that to help to better represent the three-dimensional structure of the molecule. All right, so what's the dipole? Is it polar? Well, so the thing is, if it's polar, that means we've got an asymmetric charge distribution. All right, and we do this non-bonding pair of electrons that we've got here gives us an asymmetric charge distribution, that because the groups around the sulfur are different. It's no longer symmetrical. So we are going to have a asymmetric charge distribution. So again, this is very definitely a polar molecule. Now the question is, what's the direction of the dipole moment vector? Fluorine is the most electronegative atom in the periodic table. So each of the bond dipoles is going to be toward the fluorines, and I won't draw them all here, but they're going to be that way. The overall dipole moment is the result, and if we add all the bond dipoles together, we're going to get that. And in this case, we're going to see that if you think about it and how these are going to all add together, it's going to go straight down the middle here with the negative end of the dipole pointing between the two fluorines in the equatorial plane, right? And the plus end is going to be toward the sulfur, all right? That's it. It's as simple as that. What about IF3? Same idea. We've got bond dipoles pointing towards the fluorines, and so I'm going to erase that. Again, when we add them all together, the overall dipole moment is going to go straight down the middle, all right? Averaging them all together, not averaging, but adding all those vectors together is going to give us straight down the middle. Again, pointed toward the fluorines because the fluorine is more electronegative. What about the ozone? Well, the ozone here, we've got an oxygen in the center and 2 oxygens on the outside. We know that based on that, the dipole moment vector is going to be down the center. The question is it going to have a negative end between the 2 oxygens at the bottom, or is it going to be up to the top toward the non-bonding pair? Now, non-bonding electrons will tend to counteract electronegativity, but it won't be complete. We've got these 2 oxygens here down below, and of course the up and down and all that's all relative, right? That's just the way I've drawn it. But we've got it below, we've got it down, and those 2 oxygen atoms are going to be more than enough to pull electron density toward those oxygens below, counteracting the oxygen and the non-bonding pair above, and so our dipole moment vector is going to be like so. All right. Again, all 3 of these are polar because all 3 of these have a non-symmetrical charge distribution. The presence of the non-bonding pair of electrons means that we have different groups around the central atom. So I hope this is clear. If you have any questions, make sure you ask.